Assalamualaikum, selamat pagi, good morning. This is course SIG 2004 Sedimentology, Part 1 Siliciclastics, Lecture number 5, Part 1. So today we will be looking at sediment transport and deposition. In particular, we focus more on the medium of sediment transport and deposition, and that is the fluids, right? Water, air. These media are the main agents of transport on this planet. But we'll be focusing mostly on water as an agent of transport. Okay. So this is we're going a little bit out of traditional geology here. So today we are going to talk about fluid flow, the different types of fluid, the nature of these fluids, and how they affect sediments. Okay, so going a little bit into fluid mechanics, but not into too much detail, not into deriving equations or doing any calculations. But we still need to know the fundamentals of how fluids move so that we understand how sediments move because of the fluids. Okay, so why learn about how fluids flow? Well, the main medium in which sediment is transported on the earth is water, which is a fluid, and wind is also a fluid, right? And understanding these characteristics of fluids has uses, practical uses. First, they help us solve engineering problems, things like canal construction and the maintenance of channels. These are affected by fluid flow. You might think, well, I'm a geologist. I'm not going to be involved in these kinds of projects, but that's wrong. Probably be in construction or civil engineering. You might be an engineering geologist, and some of these problems will involve a geologist. Okay, so it is also useful to understand how fluids flow when you're trying to manage, explore, or extract resources from the earth. Things like things like materials from sediments and sedimentary rocks. Fluid flow and sediment transport is linked to the formation of primary sedimentary structures. You've learned a little bit about sedimentary structures in first year, cross beds, dunes, ripples, and so on, right? And they have certain geometries and dimensions to them. We want to understand the shape and the sizes of these things, because knowing the volume and geometry of your deposits can help in mapping of certain resources, management of resources, and extraction of resources. Right? It's not just petroleum. It could be a certain kind of mineral ore. It could be water. It could be even just trying to map out pollution. Okay, so lots of uses. You need to know how fluids flow. Um, Understanding how fluids flow is also important if you want to interpret the history of the Earth. You want to know past depositional conditions. You also want to predict future depositional conditions. And to do these kinds of things, you need to know the processes which are related to, let's say, the formation of dunes or crossbeds, right? Okay? And you want to be able to simulate or make models of how fluids will move, let's say, in a channel or a strait, yeah, at long time scales or short time scales. Okay? Okay, so let's start. What is a fluid? This is a substance that continuously deforms, dia mengalir, it flows under an applied shear stress or an external force. Okay? So this includes liquids and gases. It includes water. So a fluid cannot resist any shear force applied to it. It will take the shape of its container. Okay. Um, Okay, so that's what is a fluid. So just a definition here, because I mentioned shear stress here. Shear stress is the stress component in the same plane with a material cross-section. But let's go slowly, go to that later when we meet that term again. Okay, so we know what fluids are. Fluids flow, right? They continuously deform under an external pressure. What types of fluids do you have? Well, there are different ways to classify fluid flow. So we'll look at two main ways of classifying fluid flow. First, we can classify fluids based on the motion of the fluid. All right. Second, we can classify fluids based on the behavior of the water surface. Okay. So we go one by one. We look at the fluid flow classification based on motion of the fluids first. Okay. So you can classify fluid flow based on the motion of the fluid, how it moves. And using this classification, you can divide it into three types. First, you have laminar flow, then you have transitional flow, and then you have turbulent flow. So we'll go through one by one. How do we get these three classes of fluid flow? So this is based on experiments done by Reynolds. This is Reynolds experiment. Okay. And in what Reynolds did was this. Okay. Reynolds experiments involves injecting a dye stick. So inject the dye into a fluid, and the fluid is moving at a constant velocity here. Okay, so velocity is constant. You are injecting a colored dye into the fluid. Okay. The fluid is moving at a constant velocity through a transparent tube here. Okay. So D here is the tube diameter. Then, in this experiment, the fluid type, the tube diameter, and the velocity of the flow will vary. So you play around with a tube diameter, you play around with fluid type, and you play around with the velocity of the flow through the tube. And see how two these different parameters relate to each other. Okay. And this is what Reynolds found from his experiment. Okay. So given a certain fluid with a certain diameter to your tube, right? So what happens when you vary the flow velocity, right? Now, at low discharges, at low velocities, slow moving of the fluid, you'll see that the dye in the water, in this case, follows a straight path. Okay, but when you increase the discharge and increase the velocity, your flow starts to form a wavy pathway. Okay, goes up and down, undulating at this. Now, when you further increase the velocity, further increase the discharge of the fluid coming out, in this case water, you see that the dye is rapidly mixed through the fluid, goes everywhere, flows around, and it becomes well mixed, bercampur. Okay, so you get different types of fluid movement at different flow velocities. That's the main observation of Reynolds experiment. And based on this, Reynolds classified flow types into three types based on the motion of the fluid. So here in these diagrams here, what is being imaged here is, this rectangle is a cross section of your tube filled in with a moving fluid, in this case water. It's colored blue here, okay, so water. And the fluid is moving from the left to the right. Okay, and you have these dots and arrows here with a line in between, right? So these are streamlines. You can imagine the water particles. Let's say you can actually see individual water particles, right? So you bayangkan kalau kita boleh nampak kan. So you can imagine a water particle moving from the circle to the arrow. So that's the direction, okay? So it's just a visualization, it's a streamline. So three types of fluid flow, depending based on the motion of the fluid. First, you have what is called laminar flow. Okay, and this occurs at low velocities, low discharge. Every fluid molecule, it just simply follows a straight path. Goes straight like that. Okay, so it doesn't really mix. Parallel to the boundaries of the tube. So these are the boundaries of the tube. Now, at higher velocities, higher discharge, okay, every fluid molecule follows a wavy but still parallel pathway. It's still moving roughly straight but undulating, right? Pathway that was not parallel to the boundaries of the tube. Now, at higher velocities and high discharge, every fluid molecule follows a very complex path, goes everywhere, that leads to a mixing of the dye. So you get laminar flow, straight lines, transitional flow, wavy, and turbulent flow, complex pathways going everywhere. So three types of fluids. Now, the classification can be quantified, okay, by the flow Reynolds number. So you can talk about qualitative macam gini, you can just inside your head, this is good enough for this class. Just imaging that laminar flow is straight lines, transitional is undulating, turbulent is chaotic, going everywhere. But it is also useful to quantify this, okay, using the flow Reynolds number. So this is the flow Reynolds number equation. R is the flow Reynolds number. It equals the velocity of the flow, okay, laju dia, times the diameter of the tube divided by the fluid's kinematic viscosity. All right. So just here to be more specific, what is meant by kinematic viscosity? It is dynamic viscosity divided by density. Units is meter squared per second. So if you're interested, the definitions are here. Dynamic viscosity means measurement of fluid's resistance, okay, to applied external force. Okay, you're pushing it with a force from outside. And when we talk about kinematic viscosity, we're talking about fluid resistance under the weight of gravity. Because we have gravity, it's just under the weight. So no other force from outside is applied. Okay? So that's the difference between kinematic and dynamic viscosity. Another term to use when talking about viscosity, right? In Malay, it is kelikatan. So you can imagine a very viscous fluid and a less viscous fluid, which can flow easier, right? So quantitatively, these are the values. Reynolds numbers, we call these. These are flow Reynolds numbers. So laminar flow will have a flow Reynolds number less than 1000. Okay? A transitional flow will have a Reynolds number between 1000 to 2000, and a turbulent flow will have a Reynolds number of more than 2000. Okay, so notice the relationship here. Laminar flows at low velocities, you have a lower Reynolds number. At higher velocities with turbulent flow, you have a higher Reynolds number. So notice the relationship here. U velocity is on top, right? So you can have a laminar flow. Let's say if you have a higher viscosity relative to your flow velocity. Aliran tu likat, you boleh bayangkan macam swimming bergerak kan. You can imagine wet concrete being moved. Again, it's straight lines there. It's very viscous, right? It's very slow. So that is laminar flow. At turbulent flow, you can imagine water or wind, right? So that is turbulent flow. And this happens when you have a higher velocity relative to a lower viscosity. So it occurs in usually less viscous fluids, or higher velocities for more viscous fluids. So you get a higher Reynolds number, more than 2000. Alright. So that is Reynolds number. Okay, so visually this is how this is how the flows look like, right? So this is the actual Reynolds experiment. Laminar flow usually occurs when you have a flow which is viscous or of low velocity, so you get straight lines if you put in a dye into the fluid. So that's the dye streak there in color, right? It's just straight. Transitional starts to become wavy, and turbulent is mixed. It's moving everywhere. So this occurs usually in water and air, less viscous fluids. So just an example of how you calculate Reynolds number. So let's say you have a pipe with a diameter of 10 centimeters. So at what velocity will the flow in the pipe become turbulent? Right? So in other terms, if you translate this, it comes, what is the critical velocity for R equals 2000 when it starts to become turbulent? Right? So you can determine actually the when it turns turbulent, right? At what velocity? Just by simply rearranging the equation here, right? So in this case, for viscosity, this is what we get. This is viscosity for water at 20 degrees Celsius. So this needs to change depending on your fluid. Okay. And let's say, yeah, solve this for 0.1 meter tube diameter. And this is what you get. Okay. So don't worry, all of this is on the lecture slides. I'm just showing you an example of how to calculate, how to use the Reynolds equation. Okay. Okay, so that is flow classification based on fluid flow movement, right? How the fluid flows. So you have laminar flow, you have turbulent flow, and something in between, the transitional flow. The second way of classifying flows is based on the water surface behavior. Kan? Sifat permukaan dia, cara dia bergerak atas permukaan, only on the surface, right? So based on this flow classification, you can divide fluid flow into three types. So you have subcritical flow, also known as tranquil flow, air tenang. Okay? Critical flow, in between, and then you have supercritical flow or shooting flow. And the classification is based on the determination of what is called the Froude number. Okay. So how do you determine the Froude number? F Froude number equals the flow velocity divided by what is called celerity. Yeah? But we'll go back to this later. So just look at this in terms of numbers. What is meant by subcritical flow is when the Froude number is less than 1. Okay, critical is F equals 1, and supercritical is when the Froude number is more than 1. So, okay, let's go through the equation here. So I have the slides here already. Easier to explain, right? So Froude number is determined by this equation here. This flow velocity divided by what is called the celerity. Okay. Celerity is the speed of propagation of gravity waves on a water surface. Right? So you can imagine on the surface, if you have a body of water and on the surface, you get waves moving, right? And the speed of propagation of these waves on the water surface is called the celerity. The square root of gravity times the depth. Okay. So for subcritical flows, Froude number is less than 1. So what you get is the flow velocity here is less compared to the speed of propagation of a gravity wave. Okay. So in the case of subcritical flows, we say that the water surface waves will propagate upstream because they move faster than the current. Okay, so let me help you visualize this. So let's say you have a flow of water moving down a slope. Right? So this is the bed, we call it. So that's the base of your flow. Let's say a base of a channel here. Put it yellow here, so it's solid. Then this is water. This is water. Okay, the colored blue here. And your water is moving from right to left down the slope. And the water has a velocity. All right. Sorry, probably don't use. It's not using velocity. It's talking about current speed. So this is speed. Let me correct that. So current speed. Because, so going from right to left here, you have the speed of the current moving from right to left here. All right. Then you have, let's say you imagine you put your finger into the water. Stick your finger into this water, right? So what happens when you do that? You start to get waves propagating. Right? Okay. And under subcritical flows, the waves propagating from your finger there, they are much faster compared to the current. Okay. So you can also see them moving upstream from the current. So the waves can also move towards the right. Dia lawan arus. Okay. So in this case, we say that it is a subcritical flow. Water surface waves will propagate upstream because they move faster than the current. Okay. Now you also have subcritical flows. This is when your Froude number is more than 1. Okay. And current speed is higher compared to the speed of propagation of gravity waves. So in the case of supercritical flows, the water is moving really fast downslope from right to left. Zoom, it's going very fast here. Right? So even if you put your finger here, any waves which are propagating, they are too slow, they also move downstream. You don't really see any waves moving upwards here. Okay, so that is how you visualize supercritical flow. Any water surface waves on the surface here will be swept downstream. Tak ada gelombang yang bergerak ke atas. Because the current is moving faster than the wave propagation. Okay, so that is supercritical flow. Okay, so subcritical flow and supercritical flow. So why do we need to know these things as subcritical flow, supercritical flow, Froude numbers, right? So what? So maybe for an engineer, right? But what about us? Well, these things, the Froude number affects sedimentary structures. And that is a part of the study of sedimentology, right? In sedimentology, the Froude number is important to predict the type of bed form that will develop on a bed of mobile sediment. Okay, Froude number less than 1, you get bed forms. These are three-dimensional sedimentary structures. Talk about bed forms in more detail later on, which are not in phase with the water surface. In this case, you have a tranquil water surface, air tenang, right? And then you have these bed forms at the bottom here. In this case, you have ripples forming, right? So these are subcritical bed forms. At supercritical conditions, what you get are bed forms which are in phase with the water surface. So the water has these waves here, and the bed forms below are of the same shape. They follow the phase of the waves. Okay, so you get bed forms which are in phase. So these are important when you are talking about underwater hazards, or you're trying to build constructions in water, because depending on the flow velocity, right, you can get different kinds of bed forms which affect the bed roughness along the sea floor, the seabed, or the riverbed. Okay, so just end here with with two photos just to show you bed forms which develop at different flow conditions. Now, these are just ripples, right? I made these using a flume tank in one of the practical experiments in this course, actually. It's a sedimentology course. It's just that we are under MCO, so COVID-19, so I can't really show you the flume tank experiments now, but I can show you the results here. So you have these asymmetrical ripples, and we've learned about asymmetrical ripples in first year course, right? So they are formed by a current, in this case moving from left to right, and these were formed by subcritical flow. Okay, so you have still some water here, but the water was up to here in the original experiment. I just dried the flume tank though. Now, under supercritical conditions, now this is a supercritical flow. You can see you can you can observe supercritical flows on the beach. Very easy to see them. Okay? Sometimes on the beach you have these very shallow channels, right? Notice these shallow channels on the beach where they erode into the beach, right? And the flows are very fast here, right? So you notice that you start to get these undulating standing waves. The waves don't move. The crest just stays there. Kan? Rabung gelombang ni hanya kat sini, dia tak bergerak. Okay? So these are standing waves. Okay? In this case, the flow is supercritical. Okay? Very high velocities. The current speed is very fast, faster than any waves which can propagate up. So waves cannot propagate upstream. So you start to get anti-dunes develop. So those are the kinds of bed forms that you get under supercritical flow. Two waves here, right? One here and the other one here. So there's a mound of sand at the bottom. Okay? And it is in phase with the waves. It forms a undulating, roughly symmetrical waveform. Okay? And these are what we call anti-dunes. And they form under supercritical conditions. But we'll talk about bed forms in another lecture later on when we discuss sedimentary structures. Okay? Okay, so that's part 2. There's another part after this. Okay, we'll talk about something else after this. Okay. Okay.